So, good afternoon, everybody. It's my pleasure to introduce this third lecture that is carried out in the framework of the Chaire Jaumotte. This third lecture, given again by Professor Kolmanovsky, will be on the subject of spacecraft missions. Just as a reminder, this is the third lecture. The first two lectures were more about the automotive industry. The second ones will be more concerning aerospace. In particular, today it's about spacecraft missions. And in 2 days, there will be a last lecture on flexible aircrafts. So some word about our speaker and titular of the Chaire Jaumotte for this year. Professor Kolmanovsky is a professor at University of Michigan, Ann Arbor, in one of the most prestigious aerospace engineering department of the United States. His career started in this department. Then, after having a series of fundamental contributions to the field of automatic control, he left academia for around 15 years, where he was, with various titles, involved in the research of Ford Motors. And after 15 years in the industry, where anyway he had produced a lot of results, both in the applied sense, but also theoretical, and where he was also author of more than 100 patents, he went back to academia in the same department where he studied, and it's now a professor there since 2010. So it's my pleasure to introduce these third lectures, and I invite Professor Kolmanovsky to come here.
The introduction, it's a great pleasure for me to be here. Thank you very much for your time to attend this talk. So today, this is my third lecture, and I'd like to sort of go from ground up to all the way up to spacecraft world. There's some very exciting developments in space technology that also influence what we can do as control researchers and control engineers. So control is very fundamental to those. In generally speaking, the missions that we see now in space are more involved, they are more complex. There are some very exciting developments in terms of on-orbit refueling service, assembly, and manufacturing type of missions. When I teach astrodynamics, I tell students that one difference between car world and space world is there is no gas station in space, and so that by corollary, it means that your satellite life is limited by the amount of fuel you have on board. However, with on-orbit refueling, that paradigm is fundamentally changing, and it opens up some very exciting new opportunities for what you can do. There's many more missions right now that are in Earth-Moon space, basically cis-lunar missions. And unlike satellites in LEO and GEO, low Earth orbits and geostationary orbits, where you primarily work in a setting of a two-body problem. You have a primary, which is your planet, and then you orbit around it. In these cases, you have to work with a three-body problem, which means in case of Earth-Moon three-body problem, you have to account for the gravity of the Earth, of the Moon, and then look at the motion of the spacecraft in that system. So the dynamics and the properties of trajectories are quite interesting. For instance, you have equilibria, so-called Lagrange points, and you have limit cycles, periodic orbits, called halo orbits, that are used for various missions. There is increasing attention on growing autonomy, especially for interplanetary and asteroid type missions, and that opens up new opportunities for control, and of course many developments in terms of building larger spacecraft constellations and formation flight. So just to look at a few interesting examples that I'm sure many of you are familiar with. One is James Webb Space Telescope, which was really a technological marvel in many different ways. This telescope is placed in a halo orbit, in this periodic orbit, which is near L2 Lagrange point in Earth-Sun three-body problem. And there's interesting control to be done to stay on this orbit in terms of station keeping, but also in terms of this telescope, it has a segmented mirror, and you have to align the pieces in a very precise manner to be able to take observations. So there's very interesting developments in terms of controlling this mirror. That's another mission that's quite interesting. It's a mission to an asteroid, Chaire, which is primarily consists of metal, nickel, and iron. This mission was supposed to occur earlier, but was delayed in part due to some issues discovered with GNC, Guidance Navigation Control Software. And what the spacecraft is supposed to do is to fly to an asteroid and then fly around it using several orbits and study its properties, take measurements. And as you can see, the trajectory is fairly optimized. It uses gravity assist from a flyby of Mars. I said that there is no gas station in space, but when you fly by a planet, if you do it in the right way, it acts as a free boost in your velocity. So it's an equivalent of a gas station in space if you design the trajectory in the right way. Now, this is another very interesting development with a Gateway Lunar Space Station. And this is used as a part of Artemis mission. This is in Earth-Moon system, and this space station is placed on a halo orbit around L2 Lagrange point. And it supports operations between Earth and Moon. So you could fly your spacecraft from the Earth. You can dock to this station, and then you can go to the Moon and even beyond Moon. And so there's interesting problems here in maintaining such a system operational. Hopefully, this is something that you have seen on the news. This is a DART, double asteroid redirection test. This was a sort of a test of a planetary defense mission, where the idea was to fly to an asteroid. Actually, it was a double asteroid system where there was a bigger piece here, and then there was a smaller dimorphous asteroid or rock that was orbiting the bigger piece. And what was needed to be done is to fly the spacecraft into this smaller piece. What's interesting is that when the mission departed, there was some knowledge of this asteroid, but not far from complete knowledge. So there was quite a bit of uncertainty what this asteroid is, including the shape. Of course, there has been modeling done, integrating observation data, optical observation data, extensive simulations. And last 4 hours, this mission was operating in autonomous mode. And there's guidance algorithms that make sure that you have a hit. It's actually at a fairly high relative velocity compared to the diameter of this dimorphous asteroid. And so it's quite an interesting mission where, again, control and GNC are being significantly exercised. European Space Agency is planning a follow-up mission, Chaire, where the idea would be to operate in proximity of these two asteroids, or this double asteroid, and explore that space further. Clipper mission, this is to Europa. Europa is one of the moons of Jupiter, and the reason Europa is interesting is because there may be significant amount of water, and water supports life. Now, this water is surface water, so it's not on a surface. So the idea would be to try to fly a spacecraft and essentially try to take measurements and try to confirm this hypothesis about water and other properties of Europa. This is more of an artist conception, but for exploring the surface of Europa, you may need vehicles that are different from, for example, rovers that are employed on Mars, but may look like something like a robotic snake of some kind. So the dynamics of such vehicles could be quite different. So now, if you look at a variety of missions that have occurred and being proposed, what you realize is that you need generally more intelligent, more autonomous spacecraft. And just to summarize some of the reasons for this, if you look at the communication delay, for example, to a spacecraft that near Venus, the communication delay will be several minutes. And so you cannot really operate such a spacecraft from a ground station on Earth. The delay is too large to take fast actions. There is a fairly high velocities involved. Our International Space Station moves at about 7.9 kilometers per second relative to Earth. And then if you fly spacecraft from Earth to Mars, you're at about 26.5 kilometers per second of heliocentric velocity. The other point I want to make is that the control authority is small. And what does it mean? That the forces involved, especially gravitational forces, are huge compared to what you can develop with thrust, especially with the low thrust systems that you often like to use on such spacecraft. A lot of the tools that we develop in control theory, they are based on things like feedback linearization or dynamic inversion. Well, that assumes that you actually have sufficient control authority to be able to invert the dynamics, but in these applications, you really cannot. In many, not everywhere, but in many situations, you cannot really use this tool. So you have to work together with the forces that exist in space and try to, and because of your small control authority, and whenever you have a small control authority, you have to be smart, right, about how you use what is there to be able to complete these missions and to perform them effectively. The space environment is uncertain and can be harsh. If you fly into an asteroid, the gravity field of it, if it hasn't been mapped and hasn't been flown to before, it's not known precisely. So you make some estimates, but you generally don't know what is going to happen before you have a chance of actually flying around it. If you put a lander on Venus, it cannot survive for more than a couple of hours. It's a very corrosive, harsh environment. And so this is something that you also have to keep in mind in developing the missions. And of course, you can have a variety of unanticipated issues, things like onboard failures of components, thrusters, momentum exchange devices, and we'll talk a little bit more about it. Debris or various type of obstacles that you can encounter, and various type of contingencies. So to deal with all these issues, pretty much you need a spacecraft which is quite smart and more intelligent and more autonomous. And so this is an area where some of the exciting developments at the interface between control theory and spacecraft applications occur, and there is a strong potential for further developments, of course. So what I'd like to do for the rest of my talk is to give you a little bit of flavor of some of the problems that we've been working on to address some of these challenges. Due to limited time, I don't think I will cover everything, and if you have questions, please, or I also will not go into too many details, but those details are available from publications that I typically list on the bottom, and you can email me and I'll be happy to send those you the details. So what I'd like to talk about today is, first of all, look at this issue of onboard failures and how we can handle them by taking advantage of the dynamics in control, with the idea of extending the mission operating life as much as we can. Then I view the ability to do onboard real-time trajectory optimization on board of a spacecraft as part of intelligence. So when you talk about intelligent control, you often think about machine learning, artificial intelligence, and that's very much a growing area in the spacecraft domain. There is rapidly growing number of publications and growing interest in that. And at the end, I will say a little bit about onboard learning, some of the work we've done in this area as well. But I also view the ability to recompute trajectory in real time on board of a spacecraft, subject to changing environment, as a part of having an intelligent spacecraft. So I'll tell you a little bit about work that we've been doing in this area. Okay, so let's look at some of the failures first, and I'm going to look at the reaction wheels and their failures. So coming from automotive world, cars have wheels, and spacecraft also has wheels, but they're used for somewhat different purposes. That's more a joke. So the idea is that reaction wheels are used to achieve and maintain orientation with high accuracy and precision on board of a spacecraft. The idea of reaction wheel, if you haven't seen it, it's fairly simple. It's a wheel, and it can be rotated by an electric motor in one way. And then if you think about angular momentum conservation, an angular momentum of a component would be basically moment of inertia times angular velocity. To conserve the angular momentum, if you rotate the wheel one way, the spacecraft has to rotate the other way. And if you accelerate the wheel, then it is as if you were applying the torque, right, to the spacecraft. So that's the basic idea. Now, if I have a spacecraft, it operates in three-dimensional space, and so I need three-axis control. So at the minimum, I need to have good authority over the spacecraft, I need three reaction wheels, right, to have a control of its roll, pitch, and yaw motions. Okay, so this is the basic idea. Now, it turns out that reaction wheel failures have impeded several spacecraft missions, and I'm going to put some of these missions here on a slide, and I'll mention a few of them in what follows. Probably the most famous example was the Kepler telescope that was around 2013. So you need three reaction wheels. In practice, you use usually array of four reaction wheels, and one is used for redundancy, but it's also for efficiency reasons. Something like James Webb is using 6 reaction wheels, but it has additional things. Kepler had 4, and 2 of them have failed. So now the issue is that the mission may be lost. You no longer can point it at things that you want to image because you don't have authority of the attitude control. Hayabusa is another mission. It's an asteroid sample return mission, and it's also lost the use of its second reaction wheel and remained with 2, calling into question whether the mission can continue. Now, the spacecraft can do attitude control by other means. In particular, it has thrusters, and if you have a thruster pair, you could also create a moment on the spacecraft. But the thrusters are not as precise, right, as reaction wheels can be, so they cannot be used perhaps for more precise pointing. And FUSE was an earlier mission. It was actually an observatory in low Earth orbit, and if you look at the history of failures, it has 3 out of 4 reaction wheels failed within the operational life of those reaction wheels. So it wasn't happening out of the design window. And so then the question becomes, what kind of things can you do if failures occur? Or what kind of problems you can look at, what kind of additional capabilities you can develop. So the first is really the planning. So if you plan a scientific mission and you anticipate there could be failures as you perform certain mission steps, for example, you point your spacecraft at different objects, you do orbital transfers. One of the questions you could ask, how do you maximize a science mission yield while accounting for possibilities of failures and as well as potential reconfiguration actions that you can take. We looked at that problem in the last few years, and we've modeled this type of a mission using the machinery of Markov decision processes. Effectively, you have to represent the spacecraft state in terms of what targets it already achieved and what it has not done yet, as well as state of components in a spacecraft. And then you can define sort of a yield or your scientific yield as your cost function. And then MDP provide you with a feedback policy that determines next action as a function of the mission state. Now, if you work with MDPs or dynamic programming more broadly, there's a curse of dimensionality that is a scalability challenge, and you have to look at approximate dynamic programming approximations to be able to handle the complexity, and we made some progress on that front in some of the papers that we've written. And at the end of the day, unfortunately, this table is not very visible, but you end up with extracting the rules depending on what scenario that's happening. You have the next action, reconfiguration action that your spacecraft can take. Now, the other type of a question you can look at, what can you do if your reaction wheels or other components have failed? What can you do to continue the mission? Just as an example, we can look at situations where I used to have roll, pitch, yaw reaction wheels, and my yaw reaction wheel has failed. So I have still ability to control roll and pitch, but not yaw, and I'd like to control them to desired values, pretty much zeros, which correspond to alignment of the body fixed frame and my reference frame that I want to reach. And so I have a situation where I have control about two principal axes, and my control inputs, I could think about accelerations of the reaction wheels. And so the question then becomes, can I solve this control problem? And I'm going to try to explain this without using equations. Equations are in the paper if you want to take a look at. But in control theory, a number of nice design tools rely on linearized models. So you take nonlinear model of spacecraft dynamics, you linearize it at your desired equilibrium, and then you have a linear model, and then there's a variety of methods applicable in a setting, for example, linear quadratic control. Now, the challenge here is that if you linearize spacecraft dynamics, you find that the rotational motion about each axis is decoupled, and you don't have control over yaw. So the linearized model is not going to be controllable. And that means that conventional linear controllers cannot be used. So everything we know about linear control would go out of would not be applicable in this situation. So what can be done for control? Well, there's really two potential approaches. One is that you can exploit torques normally considered as disturbances. So the space environment, there's no such thing as a perfect model in space. There's always a high fidelity model. And you base your control design on certain of appropriate fidelity model, and then you consider other effects as perturbations, and you verify that you're able to handle those perturbations. Well, in situations like this, you might look at some of the perturbations, but now look at it as an opportunity to take advantage of it. And the Kepler spacecraft is interesting. It's in heliocentric orbit trailing Earth, so there is not a lot of air drag, and gravitational perturbations, you really cannot take advantage of them from Earth. But what you can take advantage is solar radiation pressure. So there's photons coming from the sun. They bombard the surface of the spacecraft. Some of them get absorbed, some of them get reflected, and that creates a force and the pressure. And if there is a sort of asymmetry in the spacecraft, that's going to create a moment, right, that you can use for attitude control. And so it turns out that this recovers linear controllability, which means conventional linear controllers may be used in such a setting. So this is one approach. And the other approach is to say that, well, maybe we want to exploit purely nonlinear effects. As it turns out, this is actually a well-studied nonlinear control problem since the 80s. But turns out it's a difficult one. There is no continuous time invariant stabilizers. So this eliminates very large classes of controllers that are developed in nonlinear control theory. So you have to go to special methods. And we looked at a number of techniques using, in particular, switching feedback controller that achieves exponential convergence. And then when I'm going to talk about MPC, I'll come back to that model predictive control. I'll come back to that example. But anyway, some of the analysis we've done, we looked at the case of cuboid spacecraft. We analyzed linear controllability. We showed that it holds generically, but there are some singular situations where it's lost if the spacecraft is perfectly symmetric, or there is no solar radiation pressure torque about underactuated axis. But pretty much with that, we're able to stabilize the system with conventional linear controllers. The effect of solar radiation pressure is not very large, and so while you can bring your orientation to desired values, it does take time. So this is a much slower type of response that you can achieve with solar radiation pressure. And now, at the time when we sort of wrote our papers, there was also a press release that, in fact, the real mission was recovered using similar ideas, using the solar radiation pressure for control. And so that served as an indirect validation that we were on the right track with some of our work as well. Now, in terms of exploiting nonlinearities, so first of all, just to give you a geometric idea that not everything is lost if you only have two-axis control. So suppose you can roll about the body fixed axis, and suppose you can also pitch, right? So pitch, and you can roll. So if you roll, you pitch, and then you roll again, the net motion is a yaw. So pretty much the idea is that you can combine roll and pitch and generate a yawing motion. And what we did was that we would set the periodic oscillations in control variables, which is roll and pitch, enable cause a drift on average in the underactuated variable, which was the yaw. And so and then what we would do in terms of the switching controller, we would adjust the amplitude and phase of oscillations in such a way that all states, both roll, pitch, and yaw, are convergent to zero. And in this case, we assume zero solar radiation pressure torque in design, but of course our simulations account for solar radiation pressure as well. And so this is pretty much how this would look like. These are the amplitudes of the excitation. These are some of the reaction wheel speeds, and these are early angles that are brought to zero through this kind of decaying amplitude oscillations. You can do it. The previous example was with zero angular momentum, total angular momentum. You could do it also in cases of non-zero angular momentum. And there's more detailed study of that. In some spacecraft, for example, on International Space Station as well as Lunar Gateway, you would use control moment gyroscopes for attitude control. And they are a little bit different. They also involve a spinning wheel, but the velocity of this wheel is constant. But what changes is the axis of the wheel. You adjust so you change the plane in which the wheel is spinning, gimbal axis. And so as you change the orientation of the wheel, you change the angular momentum, and a change in angular momentum, it's a torque, right? It's applied to spacecraft, and that's how you control orientation in case of CMGs. Turns out you can do very similar things. If you have an array of 4 CMGs, 2 of them have failed, you could use the remaining to achieve similar goals. Now, what happens if all the reaction wheels have failed? So you no longer have any momentum exchange devices. Well, here's one idea. If you happen to have an appendage, for example, ISS has a Canadarm, right? Then you might be able to use this appendage for attitude control. And so here's an example where we have a base body and we want it to point in a certain direction. And what we are doing is that we're starting to move this appendage, both translationally and rotationally, but we are using small amplitude motion. So none of the links tries to do reaction wheel, kind of 360-degree rotation, but these are small amplitude, sometimes high frequency oscillations. And what you can then show is that suppose you start with non-zero angular momentum, so the system has been rotating initially, then you can essentially absorb this angular momentum in the motion of this pieces and stabilize the orientation of the base link to a desired pointing location. This capability is in fact not intuitive. It exploits a property of angular momentum for multi-body spacecraft, which is called non-integrability. And it's related to a falling cat landing on its feet idea or puzzle, how the cat manages to rotate in the midair to be able to land on its feet without anything to push against. And so the cat is using shape changes. It changes its shape and explores non-integrability of angular momentum to be able to accomplish reorientation maneuvers. So it arrives in the same shape, the same configuration, but with different orientation. Something like this you wouldn't be able to do with a purely rigid body type of system. And that's something that could be practical for failure mode management of satellites with appendages. Again, this is not something that's very well known. There's a number of very interesting issues concerning momentum exchange. For example, if you go to one of the science museum in Exploratorium in San Francisco, there is a momentum machine. And there is a kind of a spinning wheel, and there is a handle. And so you stand on a spinning wheel. And then if you were able to, the quality of the image was a little bit better, and you were able to read it, what it would say here is that by moving your arms around, you cannot cause the rotation of that platform. So you have to push with your foot by the floor. But that turns out not to be the case. You could actually rotate. And if you'd like to try it at home, I'm not suggesting that necessarily. You could take like a chair like this and stand on its knees. And if you move your arms in the right phase, you will actually rotate on average. And in fact, even in principle, if there was no friction, even if you started to rotate, and you could actually stop the rotation by moving your limbs. So some of this is quite interesting properties of dynamics of such systems, and they can be exploited to handle some of the failures. This is another actually work that for part of it we have actually done it in collaboration with Professor Garoni, that rotational motion can actually generate translations in the following sense, that if you happen to be in a central gravity field, if you change the orientation of your spacecraft, and here I drew it as a dumbbell, the gravity force that's acting on the piece of the spacecraft which is closer to the Earth is larger than to the one which is further away. Now, this variation is small, but it's sufficient to actually be able to create translational motions, small translational motions, by just changing the orientation. Now, the effect is not very large if you look at Earth orbits. In fact, if you want to move a couple of meters, maybe 10 meters, it will take several days for this effect to happen. This is in the relative motion sense. So you the spacecraft move along the orbit, and you sort of adjust the relative position of one spacecraft relative to where you were, or relative to another spacecraft. But if you are near an asteroid, it turns out that this effect becomes more pronounced, and you could potentially take advantage of it and actually use reaction wheels on momentum exchange orientation changes for also inducing some translational motions. We do look at some of these issues of failure mode management more systematically. It's also an area that is very well explored in the literature, of course. And we have a number of our kind of homebrewed techniques, if you like. And we try to use set theoretic methods where we think about what is it we need to do to be able to detect the modes, the failure modes, isolate them, because sometimes you take a measurement, you're able to see the anomaly, but you're not sure which component actually failed, something doesn't work. So you have to isolate it, and then you have to reconfigure, and typically you have to account for the fact that you don't have a single failure mode, but you may have a sequence of failures. And so you have to design this failure mode, in effect, management system from the start. And in terms of this set theoretic ideas, the fundamental idea that we are exploring is that you have to operate in such a way that in your current mode, if a failure occurs, then you can reconfigure in any future mode that corresponds to failure. It's sort of an obvious idea, but it allows you to design sequences of the modes and how you want to operate in each of these modes. Okay, now let me talk a little bit about the idea of onboard trajectory optimization and model predictive control and its use for space applications. But first, as a motivating factor, or at least one of the motivations for that, I'd like to mention the issue of space debris. And I think it has been well publicized that the space environment becomes increasingly cluttered. There's a lot of debris around. And of course, this is not nice because they can cause serious damage to satellites. And so the decision how to avoid debris, sometimes if you know all the debris, you could schedule that and you can control it from the ground. But in principle, you need to have a capability to, once you detect it, to be able to avoid it, as well as other potential obstacles. Some of these figures here, I just added them for reference. This is a number of debris that's increasing with time. And then I think this plot here shows the number of correction maneuvers or orbit change maneuvers that ISS has to do the number of adjustments to avoid collision with debris. So it's an issue. The two type of techniques that we've been looking at are along the lines of what we call model predictive control and extended command governors. And I think a number of people in the audience are experts in reference governors, and this is extended command governor is a type of a reference governor. Now, the idea of model predictive control, I'll try to do it almost without equations, but the idea of model predictive control is that you do real-time trajectory optimization over some horizon to the future, and then you periodically re-optimize this trajectory to account for the latest information, and you try to satisfy debris avoidance and other constraints. Now, extended command governor, for the purpose of this talk, it's a very similar scheme to MPC, except that instead of generating control input trajectory, it generates a sequence of waypoints for the existing spacecraft controller. So we're saying that there is an existing spacecraft controller, and then we pretty much change the reference trajectory to this controller. And that has a number of advantages. And then we do a number of methods to approximate constraints to simplify real-time numerical optimization. So we talk about this idea of dynamically reconfigurable constraints. Now, a couple of remarks here. If you look at the onboard processing power, on board of satellites. Certainly for larger satellites, you have ability to do computations. For small satellites like CubeSats, of course, the processing power is quite limited. But for larger satellites, you do have ability to do perhaps optimization-based control. Still, you might want to minimize the computational footprint, because even if you have computing power on board, if you run intensive computations, they're going to consume power and electrical power, and then, of course, that's a precious resource, and so you want to minimize the power that you need for computations. So in my group, we do quite a bit of work on methods to optimize the computations in model predictive control. Today, I'm not going to talk about these methods, but if it's an area that's of interest, I'll be very happy to speak about what we do in terms of numerics and how we solve these problems numerically, and what we do to simplify the computations, take advantage of approximate and exact computations, and so on and so forth. A little bit about MPC. So model predictive control, formally you could define it as a model-based feedback law, defined by the first move of the optimal control sequence obtained by solving in real-time a constraint trajectory optimization problem. So you have a model of your system. I should have put a spacecraft here, but I have an aircraft. And you have a model. You predict the response into the future over some finite time duration. And then you use optimizer to also optimize this response. If you have control inputs like thrusters or reaction wheels. And then you apply the first part of this optimized control trajectory. Then you take the new measurements, and then you recompute your control action. So you're always up to date as to what is happening. I think researchers compare model predictive control to different things, and one perspective, it's similar to playing the game of chess, because the best current control action depends on what I plan to do later. The idea is that when new measurements are available, control actions need to be updated to be able to account for unforeseen events, things like model errors, reference changes, failures, and so on and so forth. Just to show you a little bit in terms of how this might look in terms of equations. So you typically have a cost function. This could reflect your tracking errors or some economical cost that you want to minimize. You have equations of motion that you use in prediction. And then you have constraints. And one of the big reasons for using model predictive control is the ability to satisfy the constraints. And so you impose the constraints as a part of your optimization problem formulation. And then the first, this is, by the way, in discrete time. You typically convert the model to discrete time for various reasons. And then the first move of that optimal control sequence is what you use to control, and then you repeat this process. Okay, a few kind of settings where we applied these ideas. This is relative motion maneuvering with MPC. We start, this is orbital plane, so this is in track, and then this is radial position, so Earth is down there, and this is in track position. So we want to move forward in track. We want to move, yes, I think forward in track. And then somewhere in the middle, we encounter an obstacle. So we want to avoid that obstacle and then arrive at the target position. By the way, it's difficult to do experiments in space on real spacecraft, but you could kind of create videos using ground robots. And if you scale the time and space in appropriate way and then emulate dynamics and software, you could kind of at least visualize the maneuvers. Of course, this is not a real spacecraft. By the way, it's kind of interesting how the motion occurs. That you don't. This is a target. You would think that you would just move along the straight line, right? Why would you want to do something like this? But that turns out to be a more efficient way of doing things, because you go to high orbit, and the spacecraft velocity on high orbit is slower. So you let the target to move under you, and then you descend towards the target. So that also makes sense. But if you encounter an obstacle, you have to be able to avoid it, which we do using MPC. So the trouble with dealing with obstacles in a setting of optimization-based control is that they are so-called non-convex. They respond to non-convex constraints. Convexity means that I can move along the straight line, and I will not cross the obstacle. And it turns out that this is a very nice feature to have in optimization. If you have an obstacle, you cannot move through that along the straight line. You usually cross the obstacle. So that creates a number of issues, and we use various approaches to convexify the constraints. For instance, we look at something like a rotating hyperplane, where we separate the obstacle by hyperplane, and we try to stay on one side of that hyperplane. By the way, the obstacles in space, they are not necessarily of constant size, and the reason for that is because you have uncertainty. You estimate everything, right? So you run things like extended Kalman filters and more sophisticated filters to know where things like debris are. So around each object, you have typically some kind of a confidence ellipsoid, right? And your uncertainty could grow depending on where you are in orbit and which measurements you have been able to take. So it's an interesting problem where you may have to avoid an obstacle that initially was smaller, and it has become bigger. So the constraints can also be actually time varying, time dependent. With extended command governors, you can do some interesting things. For example, you can dock to a target that is rotating, and it's not doing it perhaps in the most efficient way, but the key is to be able to align this port with the docking port of the spacecraft, and so you kind of have to get out of the way here, and you can sort of do this with this type of methods that recompute the trajectory. I apologize that it's. I hopefully you can see kind of the idea of this. I apologize that I don't think it's very visible, but it will be able to now to do what it needs to do. Another class of problems where we looked at with these ideas involves asteroid landing, in particular looking at extended command governor. And the nominal controller is of linear quadratic type. Now, if you fly into an asteroid, one of the issues is that you may not know precisely the gravity field of an asteroid. So it's an interesting opportunity to try to estimate the gravity field online, or at least some correction to gravity field online, and then use it for control. And we use disturbance input observers. You could also use adaptive observers of various type. We also use various ways of convexifying constraints, rotating hyperplane not to collide with an ellipsoid, with asteroid, and then landing cone constraints. And then, so what happens here is that this dot here, it's a waypoint that extended command governor commands, and then this is a rotating hyperplane, and this blue dot is a spacecraft that is hopefully going to go into landing cone and go for landing. We looked at this with ideas of model predictive control, eventually looking at both rotational and translational motion, state estimation as well, where we use cameras to navigate. So we basically look at certain landmarks on an asteroid, and based on landmarks, we can estimate the states. And some of those details are in the papers that at least the authors' names are shown on the bottom. Here's another example where we use model predictive control for interplanetary orbital transfers. So at the moment, if you want to fly from Earth to Mars, what you would typically do is optimal control. So you would optimize the trajectory in an open loop sense. The question becomes, what happens if you have perturbations? Because you typically do trajectory optimization based on imperfect models. And then the second question is that if you recompute your solution periodically, can you improve robustness? And the answer to that is actually positive. So you could compute an optimal control to go from Earth orbit to Mars orbit. These arrows correspond to the direction of the thrust. And you're perfectly able to make it to Mars if there are no perturbations. And if you assume that there are perturbations, here we assume particularly bad thrusters. So we have thrust errors. We command the thrust in a certain direction, but it's not able to deliver the thrust in that direction. Then what happens is that we're never able to arrive at Mars, and we actually miss it. Now, in this particular case, we use the minimum time trajectory that we periodically recompute. And then with MPC, with recomputing and using initial segment for actually flying, then recomputing again, we're able to implement a form of feedback and actually able to reach Mars. It's interesting that the fuel cost that for this type of maneuver is actually lower than the optimal unperturbed. Well, this is in the case of no perturbations. I apologize. This is no perturbation case, but the fuel cost is lower, and the reason for that is because we use more refined discretization of remaining part of the trajectory. If I only have to fly 2 days, I can discretize every second. If I got a year to fly, my discretization is going to be more coarse, which is the case here. But here I can do more refined discretization. But then with perturbations, again, these are fairly large perturbations that we considered. You can actually chase Mars and actually eventually make it. Of course, the fuel cost is higher here. Now, here's another setting that we looked at. It's model predictive control for halo orbit station keeping. So these are the periodic orbits in a three-body problem. This is where James Webb telescope is at, and also the Gateway station. Now, the interesting property of halo orbits, not all halo orbits, but many of them are unstable, which means that you have to use fuel to be able to stay on those orbits. And so you have to do station keeping. And you can use MPC for station keeping on such orbits. Recently, with a few colleagues, we looked at formulations of MPC that result in, for example, lower thrust values, so that you can save more fuel while staying on those orbits. You can also do rendezvous type of maneuvers on these orbits. Here we're using a time shift governor, which is similar to extended command governor. So you have a spacecraft that you want to rendezvous to a station. And the way you do it is that you create kind of a ghost target, a virtual target for your spacecraft, and you command that as your target to your deputy spacecraft. This is sometimes called deputy, sometimes it's called a chaser spacecraft. This one is called chief or target. And so then you bring slowly this virtual target to the station, and you do it in such a way that you satisfy constraints in this mission. In particular, you want to stay within line of sight cone, make sure that the thrust is not exceeded, and when you are in vicinity of the station sufficiently close, your approach velocity is sufficiently small. So you can do it with this type of schemes. This is just an animation. There is a lot going on here, but I think it just shows the complexity of these trajectories. The target here is zero, so you look at the relative motion. This is line of sight cone, And as your velocity of the target, in this case, the target is ahead of you in orbital track, as you go through this halo orbit, your velocity changes. And so that's why you saw here, when you started the motion, you actually went backward because your target accelerated first, and then you kind of catch up. So there is quite interesting dynamics in these problems, but you can using these ideas, you can satisfy constraints. You can use this also type of schemes for formation control, in particular extended command governor type of ideas, where each spacecraft might be given a separate target, and then the targets are coordinated, so reference commands are coordinated in such a way that you avoid collisions, and eventually they arrive at a desired formation. But as they do that, there are no collisions. Now, can model predictive control control the attitude of spacecraft with two reaction wheels? If you recall, I mentioned this is actually a difficult problem. There's no continuous stabilizer for the continuous time model, so it's actually not clear that many methods can be successful for this problem. But MPC is successful. You need sufficiently long horizon, and you need a terminal state constraint. Basically, at the end of your prediction horizon, you need to add a constraint that you arrive at the desired orientation. And then you are able to control all of your early angles to the desired values. And the convergence here is exponential, which is, again, something that is difficult to achieve in this problems. But you get it basically for free, because all you have to do is pretty much change your model and say that, well, now my model has only two control inputs. I need to add this terminal state constraint and then turn the crank. And as long as I can solve my optimization problem and recompute the solution, I get a feedback law that brings me into the desired orientation. More interesting things that you can do. More of interesting things that you can do. One issue I haven't spoken about is that if you have a reaction wheel array, you have multiple reaction wheels, you also use it as a storage for the angular momentum. You have a spacecraft, and it's acting on by external disturbances, external moments, and that changes the angular momentum. Now, you don't want the spacecraft to start rotating, so you can absorb part of that angular momentum in reaction wheels. Now, reaction wheels, as you absorb more and more angular momentum into them, start rotating at higher and higher speed, and eventually you have to desaturate the wheels, which means brings them to lower speed, right? Because otherwise they cannot spin at very high speed. So how do you desaturate them? Well, typically you have thrusters. You have thruster pairs on board, so you can use thrusters, create external moment, and reduce the angular momentum of the total system. The problem using thrusters is that they consume fuel. So the question is, could you use other things? And you can use gravity gradient torques or magnetic coils and do this desaturation with zero fuel consumption. And gravity gradients, I kind of talked about them already. The idea is that if your spacecraft is kind of spread like this, you have a part of it which is closer to Earth, and here the gravity force acting on this end is higher than on this end, and that creates a moment, right? That creates a moment, and by utilizing this external moment, you can desaturate the wheels. It's a process that takes multiple orbits. But the nice thing about using model predictive control is that you can actually impose constraints on the pointing attitude of the spacecraft. So you could say that actually I want my spacecraft roughly stay in some pointing window while I'm desaturating the wheels. So that's a nice feature of model predictive control. You could also do a few things with magnetic actuators for desaturation, and we looked at this case as well. Very quickly, some other examples, now more in the domain of using magnetic rod actuators. So if you have a small spacecraft, like a CubeSat, which might look something like this, you don't have many options for for attitude actuators. For example, you might be able to pack a single reaction wheel, but maybe not an array of 4. It's just very small space, and those things are kind of cheap. But one thing that you can do is that you can put magnetic coils into the spacecraft. And the idea is very simple. You pass the current right through the coil. It interacts with the magnetic field of the Earth, and it generates a moment. Right? And so you can play with this magnetic rod actuators. Of course, look at the case at the fact that they don't generate much of a moment. So you have to make sure that you satisfy control constraints. In this particular case, we had actually a very interesting spacecraft. It was QB50 CubeSat. Was looking something like this, and it has to be flown. So if this is orbital track, it has to be flown like this because of a sensor that had to sample the very upper atmosphere. And so if you fly the spacecraft like this, this is a gravity gradient unstable configuration, meaning that any perturbation will cause you to leave this equilibrium. So you need closed loop control to be able to fly in this gravity gradient unstable configuration. And you can basically do it using MPC. Turns out you get some help. It's nice if you can get some help with hardware measures. In this particular case, there were drag panels added to the spacecraft to provide some extent passive aerodynamic stabilization. So it starts to look like a dart, right, from badminton. But you also have to use magnetic coils and control. You can try to do other things. For example, detumble the spacecraft if you only have a single coil, and you are more successful doing it using MPC than, for example, using classical, the so-called B-dot laws for magnetic actuators. I'll skip some of these details, but they're in the paper. So even if you have a single coil, at least for detumbling, so you come off the launch vehicle, and the first task that you have is to stop rotation, right? So you're tumbling, and the first thing that you want to do is to stop the rotation and then start your mission sequence. Well, if you have 3 coils, it's an easier problem. Of course, 2 coils is feasible, and it turns out that even if you happen to have a single coil, not everything is lost, and there's a number of cases where you can be successful, and we analyze this problem in one of the recent papers. If you happen to have a spacecraft that has flexible appendages, for example, some kind of antennas or solar panels, one nice thing about using model predictive control is that you can make sure that the deflections of your appendages and internal forces and moments, internal loads, they stay within acceptable range. So you try to maneuver the spacecraft as aggressively as you can, but making sure that structurally the structure doesn't disintegrate. So you can do these things with MPC. Now, one other kind of direction of research that we've exploited for a number of years is what we call maximum time or drift counteraction optimal control. And we looked at both optimal control and model predictive control formulations. And this formulations actually seems to be applicable to a number of aerospace problems. It's targeted at systems that are affected by large disturbances and dynamics causing drift. They have very tight state constraints and very tight control constraints or limited resources. And so this is a situation where eventual constraint violation is inevitable. So you will eventually violate the constraints. The only thing you can try to do is to maximize the time or some kind of yield till constraints are violated. So that's a formulation which is targeted at extending the operational life of a system that eventually is going to expire, right? And so we've looked for a number of years developing optimal control methods, but also MPC methods for solving such problems. Again, if you have interest, I'd be happy to point to a number of papers. that we have written. But just to show the applications of these ideas, if you have a satellite on a geostationary orbit, and this is the most commonly used orbit, the primary destination for communication satellites, one of the things that happens is that you are allocated some longitude-latitude window, and your satellite has to stay within this window. And to stay within this window, it needs to occasionally use fuel because there are perturbations, and they're going to try to kick your satellite out of that window. And then the question becomes, how do you manage to stay in this window with limited amount of fuel for longest possible time? And so this is the animation of the motion of the satellite. And whenever you see kind of a green arrow appearing, this is where you use thrusters. And so what's very interesting is that you don't operate the thrusters all the time. You occasionally operate them when it's optimal to do so. And you also don't always operate them on a boundary. You sometimes thrust in the interior, again, to maximize the time of staying in this window. So this is the type of problems that we have some handle on being able to do. For low Earth orbit satellites, one of the key disturbances is air drag. And that's what causes satellite orbit decay, right? That's why satellites come down eventually. And so you can have a problem where you look at how to extend your mission in staying within a certain altitude window. For example, you want to stay here while having a certain amount of fuel on board, not exceeding that amount. And so this is also a type of problems that you can solve using drift counteraction optimal control. And we've done some of these case studies as well. Then if you have a satellite with 2 reaction wheels, or even with 1 reaction wheel remaining, you might say that what would it take for me to maintain my attitude within a certain box here for maximal possible time while I have perturbations due to, for example, non-zero angular momentum and solar radiation pressure disturbances. And we looked at these problems as well. So I hope this may be an overwhelming family of examples, but it shows that model predictive control and onboard trajectory optimization can be quite useful. I just want to very briefly tell you a bit of the work that we're doing in terms of learning and exploiting ideas of onboard learning, and then I'll conclude basically the presentation. So there are a number of uncertainties on board of a spacecraft, and you can try to learn various things. In fact, you can use model predictive control also to facilitate learning. One problem that we looked at was self-learning reaction wheel alignments. So if I don't know exactly the axis of my reaction wheel, well, it's installed in some way, but perhaps it's not very precisely known, could I try to identify that axis? When you use a reaction wheel array, you have more reaction wheels than you need to control the attitude. For example, you have 4 or 6. And so you can use this redundancy to, on one hand, minimize the attitude disturbance, but on the other hand, you can sort of generate excitation to try to improve the speed of estimating this reaction wheel alignments. And the whole idea is that the cost that you use in model predictive control, the cost that you minimize, you include something like a trace of the error covariance matrix, and you can predict error covariance matrix using, for example, update equations of extended Kalman filter, roughly speaking. And then if you try to minimize such a cost, it will generate an extra excitation signal, and without this excitation signal, you're not able to improve the estimates a lot, but then you have fast conversions of the estimates with this excitation signal added. And again, if you are careful, you also tend to minimize attitude disturbance. You can't completely eliminate it, but you can minimize it. The other idea is what we call learning reference governor idea, and it's motivated by the following consideration. Suppose I don't know the dynamics of my spacecraft very well. So what can I do? Well, suppose I take my spacecraft on a side, in order to part of the orbit where it cannot collide with anything, and I try to experiment with it. I try to run it, for example, through a sequence of maneuvers, and I discover what the spacecraft is able to do. And then once I learn enough, then what I'm going to do is that I'm going to then go for a real mission, for example, try to dock to something. And so this is an idea of a learning reference governance. For a great chunk of this work, especially initial portion, we have collaborated with also Professor Garoni on this. So we pretty much run the system through command learning profiles and giving these commands to a nominal controller. And what we do is that we measure the distance to constraint violation. And based on this measurement, we update an estimate of the safe set, roughly speaking, that tells us which commands are safe and which commands are unsafe. We have two versions. One of them is what we call non-safety critical version, where you can violate the constraints during learning. And the other one is safety critical version, where you don't violate constraints during learning or after learning. Now, of course, for that, you need to know some bounds on the response of the system. This, of course, doesn't come for free, but these bounds can be conservative, and then you can combine these bounds with data to be able to improve over time. And so here's an example that we looked at, this is with a safety critical learning reference governor. So we are trying to sort of a dock to a space station, and initially we are actually quite conservative. We still don't violate constraints. For example, we stay within this line of sight cone, but then the maneuver takes long time as we're being conservative. As we proceed through this learning, we collect the data, improve this estimates. We're able to have more aggressive and quicker maneuvers that take less time. Let me skip this slide. I'll just mention that we do also work with more conventional machine learning ideas, and we're exploring some of the more conventional neural networks in some of these applications. But let me not dwell on this too much. This actually brings me to my last slide, and these are some of the concluding remarks or concluding thoughts that I'd like to leave everybody with. So I think it's clear from my beginning portion of my slides is that the spacecraft missions are becoming more complex, more involved, but also very, very interesting. And it's also clear that as we explore further and further, the spacecraft need to be increasingly more autonomous and intelligent. One of the thrusts here is to be able to extend spacecraft operational life, and this requires dealing with failures, underactuation, constrained contingencies, and ultimately limited resources. I spent quite a bit of time on this real-time onboard optimization model predictive control, and I do view this capability as one of the aspects of spacecraft intelligence. So intelligence is not only artificial intelligence, not only machine learning, deep learning, but I think also optimization-based control, ability to optimize the sequence of the decisions. It's also part of being an intelligent system. I think it's clear from examples that I've shown, and I have many more, that spacecraft control is an extensive and exciting area of control applications. And so if you're working on a piece of a control theory and you need an example, you can find one in the space domain, which will be quite interesting usually. And finally, that I should point out that certainly applications of recent advances in machine learning, artificial intelligence, as well as digital twins, is of current and growing interest. I haven't spoken, except for my previous slide about that, but that certainly is an area that more and more research will be done over time. And with that, I'd like to conclude my talk.